Okay, so thank you everyone for joining this session. We are in module 4, where we're talking about security and Wi-Fi. And today's session is the second session in module 4. And we're going to talk about authentication and encryption mechanisms, both in the personal side and an enterprise side. We'll try to cover that in more detail. And we'll also try to show you some exciting demos in today's session to explain how these protocols actually work. So before we go into details of today's sessions, let's quickly recap the last session we did. We started with the basics of security, and then we kind of covered all the various security protocols at a high level. When we said that for basic security, there are 3 main pillars for security. One is authentication, where the 2 parties that are involved in a secure communication have to mutually authenticate each other. So the sender needs to know that the receiver is the right person, and the receiver needs to know that the sender is the right person. And there needs to be mutual authentication, right? So that is extremely important. And only then we can have a secure communication between the transmitter and the receiver. So that is one of the main pillars. And then once the sender and the receiver are successfully authenticating each other, and they've both agreed that they are the right parties, that they're talking to each other, then they also have the responsibility to make sure that any communication they have between them is secure, and only they can understand that communication. And which means that they have to come up with some form of an encryption mechanism where they can encrypt the information between the transmitter and the receiver, so that anyone else who's in the middle trying to eavesdrop into that conversation will not be able to understand the conversation. Only the person who has the keys for that can understand the conversation between the sender and the receiver. And then we talked about the third pillar, which is basically the integrity of the message. It is also the responsibility of the security protocol to make sure that the information that is sent from the sender is not tampered with at the receiver side, and it's not corrupted, and it's basically has integrity, meaning there's some form of a message integrity check mechanism that various security protocols use. So authentication, confidentiality, and integrity are the main 3 main areas, 3 main pillars for security. Then we talked about the enforcers of security, basically the entities that enforce security in a wireless LAN network: supplicant, authenticator, and authentication server. And we also quickly touched upon how personal security works and enterprise security works, and what are the elements involved there. And then when we went into more detail of the various encryption mechanisms that have come along the process of the standards evolution process. So the very first version was web or wired equivalent privacy that came as a part of the base standard, and it was using a static key, which is normally 140 bits or 104 bits long, and then and it's used to encrypt the information that's being sent between the transmitter and the receiver. And we explained how the web algorithm works. There's also a concept of an initialization vector, which is 24 bits long, and then you concatenate. You basically take the initialization vector, which is a random set of bits that are generated for each packet, and then you combine it with the base key, and then you form the key that is used for encryption. And we said that web uses this RC4 algorithm that actually takes the base key plus the IV, and from that it generates a key stream. Key stream is normally the same length as basically the unencrypted text that we want to send. And then you take the key stream and the plain text, and then you XOR it, and then from there you get the encrypted text. And then you would concatenate the initialization vector for each packet along with the encrypted text, send it to the other side, and the receiver would do the exact opposite process and then decode the information. And the idea here is only the sender and the receiver have the key installed, and so only they can encrypt and decrypt the data, and no one else can. Of course, the problem is that there are 2 ways that you can basically crack that problem. The thing is that one way is, of course, if someone else has the same key, they can easily decrypt it. And second, if there is a motivated hacker, they can always sniff packets over there, encrypted packets over there. And if they sniff enough packets over the air, they will be able to see that the initialization vector repeats after a certain amount of time, and then they can collect enough information and data and do some calculations to take the encrypted text and from that figure out what the key is. And that is the vulnerability with web. And so to solve the problem, the standards body came up with an intermediate solution called WPA. WPA still uses the same cipherpass RC4 algorithm, but it is considered to be more secure than web. And we explained why it is more secure, because web takes WPA takes the base passphrase and it generates basically session keys that are unique for each session. And then there are multiple levels of keys that are generated, and the keys are also generated based on the MAC addresses of the transmitter and the receiver, so that there is a unique key that is generated for each session or each communication between a single transmitter and a single receiver. And then we also talked about WPA2, where WPA2 is fundamentally a change in how security is done, where the technology went from RC4 mechanisms to AES, which is considered to be much more advanced encryption mechanism, which is considered military grade, and it is also pretty hardware intensive to actually calculate all the information as a part of AES, which means that it needs better hardware. And so WPA is normally implemented in more modern hardware when compared to WPA, which is more of a patch-up technology for web. It's only a software upgrade. WPA2 would be a hardware upgrade, where the calculations are a lot more computational intensive. And same with WPA3. WPA3 came along a lot later, after many years, I believe in the year 2018. And WPA3 introduced even more robust encryption mechanisms and also message integrity. And the WPA3 also introduced the concept of encrypting open authentication frames. It also introduced the concept of encrypting management frames, such as probe messages and authentication messages and so on, to actually prevent any form of denial of service attacks or flood attacks and things like that. Now, regarding the attacks and everything, we'll talk more about that in the coming session, which is going to be next week. We'll talk about all the attacks and things like that. But we actually explain how the technology evolved from web to WPA3 and how technology advanced, and we discussed all those things in detail. And then we also did a short demo of how unencrypted open packets look like in a Wireshark capture, and how encryption encrypted packet looks like in the Wireshark capture. So all of that was covered in the last session. So if you missed it, the video recording should be on the website, so you should be able to go watch it. Okay, so coming to today's session, before we go into the details, let's quickly kind of summarize the concept of the three entities or the enforcers of Wi-Fi security. Coming back to this, we have the supplicant, which is basically the device, the end user device. It could be a phone, it could be a laptop, and it is one of the three components in this whole security mechanisms that we're doing. And so the supplicant software runs on the client device, and it does the client side part of the security. And then we talked about the authenticator. There's the authenticator, which is normally the access point. And if you're doing personal security, like for your home, residential Wi-Fi security, then the only thing you'll need is the supplicant and the authenticator. You'll need the client and the access point, and you can install the keys here in the client and the access point, and then the authentication and encryption happens between these two. But if you're talking about enterprise security, then we need an entity called authentication server. We talked about this last time also. We want to centralize the whole security process. So there could be several access points, and in that case, the authenticator is just acting as a relay, and it's just relaying the information between the supplicant and the authentication server, and all the security handshakes, the authentication handshakes, and everything is happening between the supplicant and the authentication server on the enterprise network. So we'll talk about that in a little bit more detail in the coming slides. This was a slide also I presented last time. We talked about WPA personal, where there's only a Wi-Fi router, and then there is a supplicant connecting the device to the internet. And then WPA2 enterprise has more entities. It has access points, authentication servers, wireless LAN controllers, and so on. And then this basically diagram here shows the various kinds of security methods. Web, WPA, WPA2, WPA3, they're all used for personal security, where you have pre-shared keys. But then methods like WPA, WPA2, and WPA3 can also be used for enterprise, and then various enterprise authentication methods can also be used in conjunction with the encryption methods like WPA2 and WPA3. And we'll talk about that in detail in the coming slides. Okay, so for us to be able to do security well when the client is connecting to an access point, the most basic thing is, first of all, the client needs to know what kind of security capabilities that the access point has. And that's the most important thing. So when the client is associating with an access point, normally this information is sent in frames like beacon frames, probe responses, and so on. And there is something called as an RSN IE, or basically robust security network information element. It's called the RSN IE inside the beacons and probe responses. So this information element contains all the details about what security standards and protocols does the access point support. Does it support AES, CCMP, TKIP? Is it supporting server-based authentication, pre-shared key? What kind of pre-shared key mechanism it's using? All the details about the security information about the access point is advertised in this particular information element. And this is the information element that the station will use to check what security method this access point is using. So for example, when you go to your phone and you list all the Wi-Fi networks, sometimes when you check a particular Wi-Fi network, it will say that the Wi-Fi network is using WPA2, PSK, or some form of security method. And that information is found from this data that the client will collect from the access point. So the RSN information element is very important, because without that, there is no chance of a client creating any form of secure connection with the access point. Of course, the RSN IE does not have any security state. It does not have any information about the keys, what kind of keys are used, and all of that. None of this is there in the RSN IE. It's only advertising the capabilities of the access point and what kind of security methods it supports, right? So that is one of the key important elements. Then let's talk about the basics of how key generation happens. If you are taking the concept of a PSK or a pre-shared key. So if you're talking about residential Wi-Fi, you have an access point, you have a client device, and you're using a pre-shared key. There is no authentication server, there is no radius server, or anything like that. So if you take that as the first example, what happens here? So this is an access point. So you can see that here there is the UI of the AP. Under the UI, in the UI, when you log into the access point, you can actually select what kind of security method you use, and you can enter a pre-shared key passphrase. And normally passphrase is plain text, and it can be like 8 to 63 characters long. And then in this case, we entered a PSK or a pre-shared key passphrase called a TP-link test. Right. So this is the only thing that the user enters, and that is the only thing that the user needs to know. All the user needs to know is this password, and so they need to enter that in the access point, and they need to enter that into the client device when the client device is connecting to the access point. Right. But of course, what happens underneath when the client is connecting to the access point is something very different. And there is so many things that happen underneath that the end user doesn't know. But there is so many layers that are created underneath, and we'll try to go through some of these details here. So the passphrase, which is the base text, then from the passphrase we create something called as a pre-shared key, which is basically a derived set of bits and bytes from the plain text passphrase that we have. So it is not easy for people to enter a large key which is long in form of hexadecimal code. Normally we don't expect people to do that. So the user is only expected to create a passphrase, and from the passphrase you create the what we call as the pre-shared key using some form of a string encoding function which encodes the passphrase, and it also takes information about the SSID of the access point, and from that it creates a pre-shared key. Right, that's the first step. From the pre-shared key, we will create something called as a pairwise master key, and this is the master key that is used for all communication between that particular client and that particular access point, and that doesn't change, it stays the same, and it is calculated as a factor of the pre-shared key, which is already calculated, plus the SSID and a few other message integrity information, and there's some form of algorithms that are developed that are used here, generate the PMK. From that comes the what we call as the PTK, or the pairwise transient key, and this is a key that is only used for a particular session that happens between this client and this access point. Now remember that this client and this access point will have one pairwise master key, but they could have multiple sessions over a period of time. So for example, this client is connecting to AP and it sends some traffic. After a certain amount of time, that session might time out, and then you might want to create a new session. So you might want to generate a new key for that new session, right? So the transient key, pairwise transient key, is more like a session key, and it is basically is going to be unique to that particular connection. So when you actually create a connection between the client and the access point, we use a process called four-way handshake, and through that four-way handshake, you create this the pairwise transient key. And when the session expires, then you'll have to redo the four-way handshake again. And then from the four-way handshake again, you generate another PTK, and it's required to have a meaningful session timeout so that it increases your security. Even though someone breaks the key from the current session, once the session times out, there is a new key generated, and that makes the system more secure. So the PTK is generated from the four-way handshake process. We'll explain what the four-way handshake process is in the next slide. And then that in turn has multiple other keys that are used for other things, like the PTK will contain something called as the KEK, or the key encryption key, and this key is used for encrypting certain type of other keys, right, that are used, right? So there are other subsequent keys that are generated, and the key encryption key actually encrypts the other keys, right? And there are other components that are the part of PTK, the KCK, the TK. TK is basically the temporal key, and that is the one that is used for encrypting the unicast packet. So all the data frames are encrypted using the TK, and there are some other components of the PTK. So just to summarize, we have the base passphrase, and from that comes the pre-shared key, which is computed by the system and using certain input variables, and from that comes the pairwise master key, and from the pairwise master key, you do a four-way handshake between the client and the access point, and then from that comes the pairwise transient key, which is a combination of multiple other keys. So there are several levels of key generation that are happening under the hood. All we did was we entered this TP-Link test passphrase, but the system does a lot of work underneath to create more of these keys. So the four-way handshake process, right? So the pairwise master key is already there, and that exists both on the supplicant side and the authenticator side based on the passphrase. And then there are four messages, right, that happen. So between the supplicant, meaning the client, and the access point. So the first message, where the access point or the authenticator sends transmits something called as a nouns, which is a random set of bits, right? And once the authenticator sends the nouns, then basically the supplicant will create the pairwise transient key on the supplicant side, on the client side. So what does the supplicant need to generate the pairwise transient key? It needs 5 things, right? The first one is the PMK, or the pairwise master key, which it already has. It's already generated that. And then it needs the nouns, which is basically the authenticator nouns message. That's a sequence of bits that is coming from the access point that it just got from message 1. And then it needs the nouns, which is also a random set of bits that are generated by the supplicant or the station. That also it generates ahead of time. It does not transmit it yet, but it generates ahead of time. So it has the nouns. And then it needs the authenticator's MAC address and the supplicant's MAC address, which the supplicant's MAC address it already has because it's on the supplicant side. The authenticator MAC address it gets from this message, because the authenticator's MAC address is the transmitter MAC address of the access point. So now it has all 5 things that are needed, and so it takes all the 5 things and then combines all of that, and from that it generates the pairwise transient key on the supplicant side or on the station side. Now that the station has created the key, it is not going to transmit that key. Remember that the PTK is never transmitted over the air open, right? Because then that will compromise the security. So the PTK is generated on the station side, so it keeps that key. And then the second message, the supplicant or the station would send what we call as the nouns, which is basically the random sequence of bits from the station side, and it sends that to the AP. So now the AP has all the 5 things it needs to generate the key. It has the PMK, it has the nouns, it has the nouns, it has the sender's MAC address, the authenticator's MAC address. So it has all the 5 elements, and it will generate, from that it generates the PTK. So now what happened is the supplicant and the authenticator both created the same key, but they have not shared the key over the air, right? And so they both use the calculations, the same calculations to generate the key. So now, as a part of message 2, by the time message 2 is done, both sides have generated the pairwise transition key. And then if the further process can involve group keys and things like that. So if you want to create a GTK, which is used for encrypting multicast and broadcast frames, then the authenticator can generate a GTK, and then the authenticator can use the key encryption key to encrypt the GTK. Remember that when we create the PTK has multiple components. It has the key encryption key, it has a number of other components as well. So the key encryption key can then be used to encrypt the GTK and send that information to the supplicant, right? And by the time the 4-way handshake is completed, the pairwise transition keys are generated on both sides. The group key is also generated and on the authenticator side and sent to the supplicant side. And now the information is all there. Both parties have the keys. Now when the supplicant sends data to the access point, it can basically encrypt the data using the keys, and then the receiver or the can actually decrypt the information using the keys. So that's normally how the 4-way handshake process works, where the transition keys are generated on both sides without actually sharing the keys over in plain text. So now we talked about the WPA personal or residential security. Now let's jump a little bit into the server-based authentication or the enterprise security, right? So as we mentioned before, on this, when we are doing enterprise deployments, it's not possible for us to install keys on each access point. So if you are deploying these access points in the enterprise, the IT person cannot go and install the keys in each access point. That is going to be a very laborious process. And if anytime you want to change the keys, you cannot go manually and change the keys in every client device on every access point. So that method doesn't really scale. So when you're doing server-based authentication, all the key management and all the authentication is all done in a centralized fashion, as I mentioned before, and all of that is pushed to a central location, and the router or the access point is just being a portal device, right? So basically what will happen is the client and the server on the network will authenticate with each other, and the access point will stay in the middle. So we want to centralize the key management and use the concept of something called as a radius server that generates the keys in a centralized fashion, and it can create unique keys for each access point, each client combination, for each session. But the key generation, key management is done by the server and not by the access point. So there are several advantages of doing this. One advantage we already talked about, which is basically the network can scale easily, so there's no scaling issue. And the second one is the overhead that is required for managing keys on the access point is going to be reducing substantially. So imagine this access point has like 50 clients connected to it, right? So if all the keys are stored on the access point, it has to now store a unique PTK for each particular client device, so that it has to save 50 keys. Even though there was only one passphrase that was entered into the AP, it needs to generate 50 keys and store all the 50 keys, because there's a unique key for each client. And that is a big overhead on the access point to manage all of that, and that overhead can be reduced if you centralize the key management. The other big advantage is the security is not attached to a particular device on the network, right? It is only attached to at a user level. So most radius mechanisms use user-based security and certificate-based security, which means that when the device is connecting to the network, it is not connecting using a key, but it is connecting using a username password. So if I have to log into an enterprise network using enterprise security, I would put in my login information, my username, password, credentials, instead of putting a security key. Because the security key, if someone knows about it, they can put it on any device, and the network is compromised. If someone steals my device, most likely the security password is already entered. here and it will compromise the device. But normally usernames and passwords can move with the user, right? So I will keep my username and password and I can log in from multiple devices. So the user-based than device-based management makes security a little bit more robust in many ways. So these are some of the advantages of using server-based authentication. So now let us talk about this entity called the server. Normally, we have many different types of authentication servers. We also refer to them as AAA servers. The most common one that is used is the Radius server. Radius stands for Remote Authentication Dial-in User Service, and it does basically three main functions, right? It does the authentication, which means that it does the mutual authentication between the client and the server. It does the authorization. So there's an authorization steps, which is basically, you can think of it as somewhat like a firewall functionality, right? So for example, it will authorize every user that's coming onto the network. Not only is it going to authenticate them, it will check if they have after they've authenticated, what kind of privileges do they have? Are they getting access to everything on the network? Are they going to get access to only a specific part of the network? Do they have any restricted websites or things like that they cannot go to? And there is a number of other things that are based on physical location, for example. So if you are in a particular office or a particular physical location, you might have some restrictions and some some restrictions that are applied. So all of these things are a part of authorization, right? And also time of access. So how long you have access. So for example, let's say you're connecting to a Wi-Fi network in an airport, and there is a limit. There's a time limit. Let's say 30 minutes, right? So you can also create authorization based on time limits and things like that. So that's an authorization function. And then the third one is the accounting function. It is not very commonly used in the enterprise space, but if you are using monetizing things over Wi-Fi networks and things like that, then of course, if the customer is paying for Wi-Fi connectivity, then there is some form of accounting that we need to do, right? Billing, management, planning, those things also can be implemented by the Radius server. The Radius server can track how many minutes that the user is on the network, and based on that, they can basically do billing and prepaid, postpaid plans and things like that. All of that can be essentially installed on the Radius and done on the Radius server. It's not normally done in Wi-Fi networks, but that is also something that can be done. So normally Radius server is used for authentication, authorization, and accounting, and it's called the AAA server. This is an important entity in enterprise security. Another important element of enterprise security is what we refer to as a certificate, a digital certificate. Normally, clients and the authentication server exchange some form of a digital certificate. So digital certificate is you can think of it as a digital way of validating someone, right? So for example, if I want to hire someone, an engineer, then I'm going to look at the resume and I want to see what certificates they have. Like, okay, so I want to hire a network admin. So I'm going to say, oh, they have a CCNA or a CWNA certification or something like that. And there is a certificate that comes with it. So that gives me some proof that this person is a valid person that can do the job for me. And so we're all used to the concept of certificates. The idea of a digital certificate is for any particular website or any organization, you can use some form of a public key, and you will take all this in the information about the user and things like that, and you can create basically a certificate that is used for mutually authenticating the client and the server. Normally, certificates are used for when you access a web page and over SSL and other mechanisms. You have some form of certificates that are used. And normally, certificate contains information about the organization. It's a public key, and who issued the certificate. There's a certificate signing authority, and then other details about the certificate. So normally certificates are also used for authentication process or mutual authentication process in the enterprise network. Okay, so if you look at how the server-based security works, again we look at the same three entities: the wireless station, the access point, and the authentication server. And there are multiple packets that are exchanged between all these three entities. Normally, the communication between the wireless station and the access point uses this mechanism called EAP over LAN. protocol which runs on top of 802.11 on the Wi-Fi side. And these are all the exchanges between the wireless station and the access point. The exchanges between the access point and the authentication server use the radius protocol, and they're also, of course, done on top of normal UDP over IP networks, right? And then this entire communication between end to end is normally referred to as EAP, or extensible authentication protocol, as a part of the .1x authentication. So this is kind of basically how enterprise security works. And that is if you look at step by step the process, the first step is the station connecting to the access point using the base .11 connection, right? So we all remember how a station connects to an access point. So station sends a probe request, the access point sends a probe response, and in the probe response it has the RSN Information Element, and it also tells what kind of security it supports. And then you can use the normal open authentication, which is basically authentication request, authentication response, and then you do normal association, where association request has the RSN capabilities, IE capabilities of the station, right? And then you have the association response. So this is the base .11 connection. This is mandatory for any kind of security. The first step of creating a secure connection is to first create a base .11 connection between the wireless station and the access point. Once this step is done, then you would go with the authentication process. The authentication process is now between, so now we know the station is connected to the access point. So this connection is done at the .11 level. This is at layer 2, right? But then the next step is the station needs to authenticate with the authentication server, and the authentication server needs to authenticate with the station. So that is where the EAP protocols and the .1x protocols come into picture. And so there is a whole process that happens here, which we'll explain in the coming slides, where the client will exchange certificate information with the server. The server will send certificates to the client, and then they will mutually authenticate each other. And then once that authentication step is done, then the station and the access point will be generating the PMK, right? So the user doesn't enter the PMK in this case. And then that, based on the authentication process, there is a process to create the PMK automatically on the station side and the AP side. So we'll show that in a demo that we're going to show later in this session. And so automatically the PMK is generated, and then the next step is the keys, generating the keys from the PMK, which is our standard 4-way handshake process that we already discussed. So, and then the next step is the 4-way handshake. Once you do the 4-way handshake, then you have the keys for each session that between that particular station and that particular access point, and the encryption starts. So this is the entire process of .1x authentication or server-based security. So this is again summarized here in this slide. If you're looking at .1x authentication, you have the 3 entities here. Again, you have the supplicant, the authenticator, the authentication server, and they all exchange these messages. So basically the supplicant will basically send a EAP start message to the authenticator. The authenticator will send a identity request asking the supplicant for its identity, and then the supplicant will respond with its response, and then that information is relayed onto the radius server, which is basically the authentication server. This protocol is EAP over LAN, and this protocol is radius over UDP, right? And so this is all happening over the wired between the access point and the authentication server. This is happening over your Ethernet connection, right, or the wired network. And then the authenticated server will send some form of challenge to the supplicant. It could be in the form of certificates, information, and things like that. The supplicant will respond, and then there is going to be this mutual authentication, as I mentioned before. And then once all of that successfully completes, then there is an EAP success message, and this is how the entire handshake process will work. So now, taking an example of one of the methods, there are many methods used, and one of the methods, are considered the more secure method, is what we refer to as EAP-TLS, right? And the EAP-TLS message basically is one of the secure methods where you actually exchange certificate information between the client and the server. The client sends its client certificate, the server sends its server certificate. We're going to show that in a demo that's coming up. And then the mutual authentication happens. As I was saying, it is a more secure method. There is more robust analysis here between that, the server certificate, client certificate exchange, and things like that. and then the four-way handshake process happens, and then the encryption channel gets open, and then the encryption will start. So I'm not going to go into the details of all the messages, but certainly you can refer to that from this slide. Similarly, there are more complex methods like EAP-PEAP, EAP-MS-CHAP, and so on. And these are also, some of them are challenge based, some of them are username password based, some of them are certificate based. So there are many methods, but the base process is the same. So it is the supplicant talking to the authentication server through the authenticator and exchanging all the information to mutually authenticate with each other. Now, different operating systems and different organizations may use different methods. So that can be different for different people. So this is an example of how the connection handshake actually works. We are actually planning to show you a demo right now. So I'm going to skip these things, but you can see from the Wireshark captures that how the base .11 connection happens, the .1x connection happens, and the four-way handshake happens. All those details can be seen here, but we're going to show you a live demo now of how this works. So there are these various EAP methods, like as I mentioned before, EAP MD5, LEAP, which was one of the proprietary Cisco protocols. There is EAP-TLS, EAP-FAST, which is a faster mechanism of doing EAP. There is EAP-TLS, which is tunnel TLS, which is considered to be even more layers of security. There is PEAP, MS-CHAP, and multiple versions. These are all the various types of security, .1x authentication security mechanisms that are used all around the world. They have all their own advantages, disadvantages. Some of them are fast, some of them are slow, some of them take a lot of time, some of them are more secure than others, and different IT organizations use different security methods on the server side. So that's just a quick high-level overview of enterprise security and also four-way handshake and all these other things. There are some references here. And I'm going to end my session a little bit earlier so that I give the chance to our team to actually show a demo. And they're going to walk you through how a four-way handshake works and show you some packet captures and also explain how the enterprise security works and through packet captures and so on. So over to you, Gopi.
Okay, if you understand what Sitaram sir said, so there are two different types of authentications, right? So one is pre-shared key authentication. That means, so one key will be shared to all the clients in the network. Okay, so using this key, everyone in the network will use the same key to connect to the access point. Okay, so here in this demo, we are going to use a LAN Forge as a client device. So it's okay if you use your mobile phone, that's okay, or else anything. So you can just use your password, like how you connect to the network, and then you just connect to a network, right? So, or else there is another method you can use is 1x enterprise authentication, right? So here you use a radius server as a authentication server to verify your identity. Here access points is not going to do authentication part. Okay, it will help you to generate the keys. Okay, that I will show you in this demo. I hope if you understand these two methods. So I will jump into the PCAP. There you can see the connection process between the client and an access point, the basic authentication. Okay, if you see this packet capture, okay, here is an AP and the client. Okay, and till here, till this association response, what you did, you exchanged the capabilities of client and an access point. Okay, then that means, okay, access point will say, yeah, you are capable and I can manage you and I support all your capabilities. Okay, that means enough. Okay, now, so in the basic connection here, that means the client device and an access point will have the PMK. PMK means that will be generated from the passphrase that you have. So only if you have the passphrase, that means password, like if you use 128, that's your wish. It will be very easy to crack. Okay, so then from that password, it will generate the PMK. Now, is that enough to encrypt the packets? No. As sir said, you need keys, different keys to encrypt the data. So in order to generate those keys, you need four-way handshake. Okay. So four-way handshake will be exchanged between access point and the client. The four messages, it contains different types of data. I will show you. Okay. In the first message, if you see, okay. So in order to generate PTK will be derived from the PMK. So in order to generate the PTK, what you need uh, anons, snons, and the client address and AP address and the PMK. If you have the password, you will have PMK. That's it. Okay. So what what is missing to the client to generate its PTK? It's only anons. Okay. So anons will be sent from the AP. This is the anons. The first message from the AP to the client will be sent, and it contains the anons of AP. Okay. So now here in this part, client has everything to generate PTK. Okay. It has anons and it will generate its snons. Okay. And it will generate it as snons and everything it has, and it will generate the PTK. Okay. And it will reply to the AP in key 2 message. Okay. In key 2 message, it will send snons to the AP and also a mic. And I have seen the question in the Q&A section. So how these keys will be verified? How AP will verify this client is generated correct PTK or not, right? So using this mic. So once AP receives this snons, now AP has everything to generate PTK. Okay. Now AP will take this snons and it has PMK, snons, anons, and as well as MAC address of each one. Okay. Now it will use this information and generates the PTK. Okay. So if you observe this mic so is used to verify the PTK generated by the client. Okay. So now once AP generates the PTK, it will check this mic is valid or not. Okay. So it will just if the mic matches, then it says okay, the client is verified. Okay. It generated correct PTK. So that's why I'm able to match this mic. Okay. So if you give wrong password, then the PMK will be different, and from that PMK you will generate a different PTK. So if you send mic with a different PTK, then the AP can't verify this mic. Then mic will be different, and it won't respond with the uh, third message. Okay. Now, so if you observe this third message, the third message um, will be sent from AP to client. It has MIC from the AP and this WPA key data. What does that mean? Okay. So this data is looks like it is encrypted. If you observe, it's encrypted. So how it is encrypting? So if you see, if you see, PTK consists different types of keys like temporal key and KEK, that means which is used to encrypt GTK keys. Okay. So let's decrypt this. Just to check what information inside it. Okay. Let's go to IEEE and enable decryption. I have already added my keys here. Okay. And just say okay. Okay. If I see this information, it has RSN information of AP. Okay. We don't need that. And if you observe the GTK and IGTK. Okay. Let's talk about GTK now. So GTK you have seen, right? So GTK is used to encrypt the broadcast or multicast traffic. Okay. So someone asked in the Q&A section, So if I want to transfer only unicast, does I need GTK? Yes, absolutely. You don't need GTK in order to only use unicast traffic. So GTK will be used to encrypt or decrypt the broadcast or multicast traffic. And if you see IGTK, this key, when you enable 802.11w, and this key will be used to encrypt or decrypt the broadcast or multicast management frames, only management frames which will be broadcasted or multicasted. So yeah, from this message it will send to the client. So once client install all these in his device, then it will say success message with a make. That's it. So but in the last session, if you have seen, so I was able to decrypt my colleagues data, right, using my password. I mean, because see, this is what his data. Okay, how I decrypted. So in order to decrypt his data, what I need PMK. PMK will be derived from the password that I already have. As an employee, I have that. Okay, and what I need anons and snons. I got this from this. If you sniff while he's connecting to an access point, you will get these two messages. So from if you have these two, and you will have everything. You will have this is client address and AP address, and you already have PMK. So and if you miss any of this, then you can't able to decrypt. If you miss snons or anons or these four-way handshake, then you can't able to decrypt others data. So here why we need 1x authentication. So I was able to decrypt my colleagues data, but it's not good, right? But so that's why we need to use 1x authentication. So here as sir said, there will be different methods, heap methods you can use. I tried with the TLS and TTLS. Okay, let's get into TTLS. How the connection process between client access point and the authentication server. Okay, so here only we use client device and access point to connect and generate the keys, but here we use radius server as the authentication server. So this will verify the client device is valid or not. Okay, and it's not going to generate keys, PTK keys. Access points will generate and generate the encryption keys, but we use radius server as a authentication server. Okay, okay, let's get into the PCAP. Okay, so if you observe this, the same normal procedure what we followed. Okay, till here API and client will check their capabilities, and if it's capable, then okay, it will give association response. From after that, here AP will ask the client its identity, because so in enterprise each client will have different username and password. Okay, they use their individual username and password to connect to an access point, then only you will get access to the network. Okay, so if you use same, then you will have same PMK, and again you can able to decrypt others data. That's why we use 1x authentication. So and AP will ask for his identity, and now client will provide his identity. So my identity is Gopi, and I have given Gopi as my identity. And it will ask, oh, okay, what method you want to use. Okay, it will send, it sends me that MD5 challenge, but so I'm using TLS, right? So I will say NAC, negative acknowledgement. No, I don't support your MD5 challenge. I support TLS. Okay, then again it will request whatever the method you support, and once it's done, then client will say hello, and also it will say what are the ciphers it supports. Okay, if you open this, okay, it will say different ciphers it supports. You can if you support any of this, then we are good to go. That's it. Okay, then after that, server will say hello. Okay, here the server hello. It contains, what it contains is, let me show you. Okay, it will say server hello and the cipher. Okay, it will share one cipher that it supports, and it will share his certificates. Okay, all his certificates. Okay, TLS certs, and it will exchange the key. Okay, that means it will exchange the public key. So in the starting of this authentication, both client and AP will have their public IP and private key. So they will exchange the public keys. Okay, and it will ask for client certificates. So it's requesting, the server is requesting to the client, share me your certificate to validate. Okay, that's it. And in the next response, it will share the certificate. So if you see from the client to AP, it will share its certificates, and it verifies the certificates using a signature. It will share the signature, and once this done, this success message, once Radius server validates the client, then Radius server will generate the PMK and not the AP. Okay, so it will send that PMK to the client, and now client to the AP. Now AP and client has PMKs, right? So once AP got the PMK from the Radius server, then using that PMK, it will generate the same. It will generate the PTK using same four-way handshake. So if you open, then same, we will have S nonce, A nonce, then they will just exchange. And so because of this method, EAP method, so each client will get different PMKs. So even if I sniff Synapse data, I can't decrypt it because he is using his credentials. If I have those credentials, I can able to. Okay, but if I don't have, then I can't. So that is the important why we most of the enterprise networks use this EAP method. Okay, so how I did this test is using LANforge. Okay, so even you can use your mobile phone. You can if your AP supports WPO2 enterprise, then you have to create some Redis server. You can go and search in the internet then how to configure it. And once you do that, and you just have to pass these certificates. Okay, here you have to pass the identity and the password and the certificates that you have in the TLS case. I have also done TTLS. So what is the difference between EAP-TLS and EAP-TTLS? Here both in TLS case, both client and the AP authentication server should exchange their certificates, and both need to valid. Okay, and in the TTLS case, only server has to exchange the sets to the client, and client doesn't need to exchange its sets. That's the only difference. It says, yeah, and so if you use TTLS, you don't have to provide any certs here, and that's it. You can just connect your client.